Bismillahirrahmanirrahim. My dear student, I am Dr. Muhammad Yaseen. Today we are going to discuss a very important topic of chemistry, that is the pericyclic reaction. Always remember that the pericyclic reactions are very important, not only from the examination point of view but as well as from the synthetic point of view. I have not seen any of the chemistry examination in which people have not asked about the pericyclic reactions. So what are the pericyclic reactions? It is a fundamental lecture about the pericyclic reactions. In the coming lectures I will teach you what are the types of the pericyclic reactions and how they differ from each other. So let's move towards our topic of pericyclic reaction. So this is our first lecture on the pericyclic reactions. It belongs to the organic reaction mechanism course of the BS6 chemistry. Here is a list of the key concepts that we are today going to learn. We will first learn what are the pericyclic reactions. We will go through the definition of the pericyclic reactions and will study their characteristics. We will also study the types of the pericyclic reactions, how many types of the pericyclic reactions are there. We will study the symmetry of the p orbitals, since there are two types of symmetries of the p orbitals, namely mirror plane symmetry and the center of symmetry. We will go how these symmetries are assigned, and at the end of this lecture we will learn how one can assign the symmetries if multiple number of the p orbitals are present. So this is a list of the key concepts of the today's lecture. So let's move towards the definition of pericyclic reactions. The word pericyclic composed of two words. Peri means in all directions, mean all around, and the cyclic mean in a circle. So in organic chemistry, pericyclic reactions are defined as those reactions that proceed through concerted, I am saying concerted cyclic shift of pi electrons. So I have the two key points that I have emphasized during the definition of pericyclic reactions is that the reaction should be concerted. What is the meaning of the concerted reaction? Concerted means that the bonds of the reactants and the products are broken and formed at the same time. That is, the bonds of the reactants are broken at the same time, whereas the bonds of the products are forming at the same time. So the concerted means the bond of the reactants are broken and the bonds of the product are formed at the same time through a transition state. So the formation of a transition state through which the bonds of the reactants are broken and the bonds of the product are formed at the same time is a characteristic of a pericyclic reaction. The second point that I have used in the definition of the pericyclic reaction is the cyclic shift of electrons. So the pi electrons of the pericyclic reaction moved in a closed circle. So all the pi electrons moved in one direction in a closed circle. So we may say that in organic chemistry, a pericyclic reaction is a type of organic reaction wherein the transition state of a molecule has a cyclic geometry. The reaction progresses in a concerted fashion and the bond orbitals involved in the reaction overlap in a continuous cycle at the transition state. So the two key points are that the pericyclic reaction, the reaction should be concerted. Concerted means the bonds of the reactant are broken at the same time when the bonds of the products are forming in a transition state, and additionally the pi electrons move in a cyclic manner or in a closed circle. So these two characteristics, if you see these two characteristics in a chemical reaction, you may say that this is a pericyclic reaction. If only one of these characteristics is found, it is not a pericyclic reaction. Both these characteristics should be found in a chemical reaction for it to be declared as a pericyclic reaction. So now let's move towards some definition and see whether these are a pericyclic reaction or not pericyclic reaction. So in the first example, you may see a reaction between a dienophile and a diene resulting in the formation of a cyclohexene. So what is a diene and what are the dienophiles? Dienes, as the literal meaning, di mean two, ene for alkene. So in the example you may see a diene having the two alternative double bonds. And a dienophile is a compound that loves the dienophile mean the one substance who loves the diene. So the dienophile readily attacks on the diene. That is why it is called the dienophile. So here in this case, it is an example of pericyclic reaction. I have not shown the transition state. However, on this reaction, on this slide, you may see the red colored arrows showing the cyclic movement of the electrons. Here the pi electrons are moving in anti-clockwise fashion. You may also move the pi electrons in the clockwise fashion. However, the result is the same, that is the cyclohexene. It is Diels-Alder type addition reactions. Diels-Alder type reactions are a type of a pericyclic reaction that we will discuss in the other part of this of the lecture. Diels-Alders, it is a reaction between a diene and a dienophile. So in the example number 2, you may see that the pi electrons are moving in a closed circular manner and resulting in a cyclohexadiene. So a cyclohexadiene is formed. Here again, pi electrons are moving in a cyclic movement. In what direction they are moving? They are moving in the anti-clockwise direction. Here I have, in these two examples, I have not shown the transition state, and it is showed that the electrons of the reactants are broken and the bonds of the product are formed in a transition state at the same time. So these two reactions obey the concerted mechanism. Concerted mechanism means the bonds of the reactants are broken and the bonds of the product are formed in a transition state at the same time. So both these reactions are a type of a pericyclic reactions. The first one is classified as a Diels-Alder type addition reaction. So the second time is the second example is the example of a ring closure, ring opening type chemical reactions of a pericyclic reactions. The cyclohexadiene, here you may see that hexocycladiene is formed from a triene. This cyclohexadiene may also be decomposed into a hexatriene. That is why it is termed as ring closure, ring opening reaction. Here I have shown you a third example of a pericyclic reaction. It is an ene reaction in which an alkene, or here in this case a molecule of ethene, is attacking on a molecule of propene, and the molecule of propene is in turn attacking on the molecule of ethene, resulting in the formation of a molecule of pentene. So here you may see that the pi electrons of ethene and the propene are moving in a circular manner, and here in this example they are showing a clockwise movement. So since the electrons are moving in a clockwise manner and also this reaction is concerted, so this is an example of a pericyclic reaction. So all those reactions in which the pi electrons move in a clockwise manner or anti-clockwise manner, or you may see that they show a circular movement and the reaction follow a concerted mechanism. All those reactions in which the bonds of the reactants are broken and the bonds of the product are formed at the same time are called the concerted mechanism. So this is an example of a pericyclic reaction. So one very important question comes that from where these reactants obtain the energy for the conversion into the product. So the question is how these reactants, or from where these reactants obtain the energy for their conversion into the product. They got energy either through the answer is they got the energy either in the form of photons or light or through the thermal energy. So there are two pathways to obtain the energy. One is the photonic energy or the light energy, or the second path is the thermal energy, and hence the reaction is said to proceed by obtaining the energy either from the photon or from the thermal energy. The very important characteristic of the pericyclic reaction that you should never forget, I am saying that you should never forget, that pericyclic reactions are stereospecific. So what is the meaning of stereospecific? So let's move towards another slide and we learn what is the meaning of stereospecific and how the pericyclic reactions are stereospecific reactions. What are the stereospecific reactions? In order to study the stereospecific reaction, let us consider following three examples. In the first example, you may see that a molecule of a 2,4-hexadiene upon absorbing the thermal energy is converted into trans-3,4-dimethyl cyclobutene. In the product, you may see that the two methyl groups are in the opposite direction. So whenever you proceed the reaction of 2,4-hexadiene by the absorption of thermal energy, you will always obtain a molecule of a trans-3,4-dimethyl cyclobutene. You will never obtain a cis molecule of 3,4-dimethyl cyclobutene from the molecule of 2,4-hexadiene upon the absorption of thermal energy. So this is a stereospecific reaction, since the molecule of 2,4-hexadiene upon the absorption of thermal energy give only a molecule of trans-3,4-dimethyl cyclobutene. So it is a stereospecific reaction because it is not giving the cis form, it is give only one type of the product. Let us consider another example. In the second example, I have shown a molecule of 2,4,6-octatriene. The molecule of 2,4,6-octatriene upon the absorption of thermal energy give a molecule of cis. In here, you may see that both the substituent of methyl substituent are on the same side, and I have shown it with the black wedged bond. Both the methyl group are on the same side. So upon the absorption of thermal energy, a molecule of 2,4,6-octatriene is producing a molecule of cis-5,6-dimethyl cyclohexadiene. It is not producing the molecule of trans-5,6-dimethyl cyclohexadiene. It is only producing the molecule of cis-5,6-dimethyl cyclohexadiene. So it is a stereospecific reaction. On the other hand, when the molecule of 2,4,6-octatriene is given the photon energy, or given the energy through the photon, or when light is thrown on this molecule gives a molecule of trans-5,6-dimethyl hexadiene. So whenever you proceed the chemical reaction of 2,4,6-octatriene through thermal energy, you will always obtain a cis product, and when this molecule is converted into product via the absorption of photon energy, you will always obtain the trans product, not the cis product. So these are the example of the stereospecific reaction. In the stereospecific reaction, only one type of product is obtained, only one type of stereoisomer is obtained under a set of certain conditions. So I hope you have learned what are the stereospecific reactions. Suppose if you have a molecule A and you are giving the energy and it is converting into B and it is converting into the cis and trans isomers equally, so it is not a stereospecific reaction. In the stereospecific reaction, you will obtain only one type of the product under the given set of conditions. So all the pericyclic reactions, I have informed you in the previous slide that all the pericyclic reactions are stereospecific, mean you will obtain only one type of the product in a preferred manner. Here on this slide I have shown the summary. So what we have learned up to now, we learned that the pericyclic reactions follow concerted reaction mechanism. They show cyclic movement of pi electron, and that the pericyclic reactions are stereospecific reactions. So this is what we have learned so far. Concerted reactions are those reactions in which the bonds of the reactants and the bonds of the products are broken and formed simultaneously. That is, the bonds of the reactants are broken and the bonds of the products are formed simultaneously. Cyclic movement of the pi electrons mean the pi electrons, all the pi electrons of the reactants move only in one direction or in a circular manner, and that the reactions are stereospecific mean that under the given set of conditions only a one preferred form of the stereoisomer is obtained. So these are this is the summary of the pericyclic reaction that we have learned up till now. So let's move now what we are learning new about the pericyclic reaction. When we talk about the types of the pericyclic reactions, there are 4 types of pericyclic reactions named as electrocyclic reactions, cycloaddition reactions, sigmatropic reactions, and lastly the group transfer reactions. Group transfer reactions are also named as the Yeen reactions. Before we go into the discussions of each type of these pericyclic reactions, first let's have look into some important definitions. Before going into the detailed discussion of pericyclic reactions, let's have the definition of some important points. First one is the symmetry. What is symmetry? Mathematically, symmetry means that one shape becomes exactly like other when you move it in some way, for example, turn, flip or slide. For two objects to be symmetrical, they must be the same size and shape, with one object having a different orientation from the first. There can also be a symmetry in one object, such as face-to-face symmetry. However, there are major 4 types of symmetry. These include the translation symmetry, rotation symmetry, reflection symmetry, and the glide reflection symmetry. While studying the pericyclic reactions, you must have the knowledge of symmetry of p orbital, since in majority of the pericyclic reactions you will be encountered with the p orbital, since the pi electrons reside in the p orbitals, and I have already told you that in the pericyclic reactions pi electrons move in a circular manner, so you must have to know the symmetry of the p orbital. You will see the 2 types of symmetries among the p orbitals while studying the pericyclic reaction. So the p orbitals have 2 types of symmetries. A p orbital may have 2 types of the symmetries. It may have M1 symmetry. Number 1, M1 symmetry, and number 2 is the C2 symmetry. So the p orbitals may have either a M1 symmetry or C2 symmetry. What is M1 symmetry and what is M2 symmetry? M2 symmetry means mirror plane symmetry. What is a mirror plane symmetry? We will discuss in the later section of this lecture. And the C2 stands for the center of symmetry. So the p orbital, your p orbital involved in the pericyclic reaction must have either M1 symmetry or it have the C2 symmetry. M1 symmetry stands for the mirror plane symmetry, and C2 symmetry stands for the center of symmetry. What are the M1? What are the M1 symmetry and C2 symmetry? Let's discuss that. In order to understand what is M1 symmetry and C2 symmetry in the p orbital, let us consider the diagram on this slide. In the diagram number 1 that is present on the left side of this slide, the 2 p orbitals are present. Each lobe of the p orbital is assigned a sign that is either it is sign positive or negative. The positive sign is the sign of the wave function. It is not the sign of the charge of the proton, and similarly the negative sign of the lobe of the p orbital is the sign of the wave function of electron, and it is not the charge of the electron. So the two p orbitals present in the picture number 1 on this slide are the mirror image of each other and are superimposable to each other, and hence these 2 p orbitals, in these 2 p orbitals, the positive sign bearing lobes are on the upper side and the negative sign bearing wave functions of the lobes are on the lower side, and hence they are said to possess the M1 symmetry or mirror plane symmetry, since these are the mirror plane of these are the mirror image of each other. So all those p orbitals in which the positive sign bearing lobes are on the same side and the negative bearing lobes are on the other side and are in front of each other are called to possess the M1 symmetry. So here in the picture number 1, the 2 p orbitals possess the M1 symmetry. Whereas in the second example, or in the second picture that is present on the right side of this slide, the 2 p orbitals having the positive, one is having the positive lobe on the upper side and the other is having the positive lobe on the lower side, and similarly the one is having the negative lobe on the upper side and the other is having the negative lobe on the opposite side, and hence they are said they don't possess the mirror plane symmetry. what kind of symmetry they possess? They possess another kind of symmetry that is called the C2 symmetry. What is C2 symmetry? We will discuss it in the coming slide. So the summary is that all those p orbitals which are the mirror image of each other, that is, they are having the positive sign bearing lobes on the same side and the negative sign bearing lobes on the same side, are said to possess the mirror plane symmetry. In figure number 2, p orbitals are not the mirror image of each other since they possess the signs of the lobes on the opposite side. So what kind of symmetry these orbitals possess? My question is, what kind of, they possess another kind of symmetry. What kind of that symmetry is? Definitely, I have already informed you that there are two types of symmetries in the p orbital. One is the M1 symmetry and the other is the C2 symmetry. So they may possess a C2 symmetry, either they possess a C2 symmetry or not. Let us discuss it. Here in this picture, I have shown the two p orbitals. One is having the positive lobe on the upper side and the negative lobe on the lower side, whereas the second p orbital is having the positive bearing lobe on the lower side and the negative bearing lobe, sign bearing lobe on the upper side. These two p orbitals are separated through a mirror plane. The center of this mirror plane is shown with a small circle. If one goes on opposite sides at equal distance, you will need the same sign of the p orbital. So these p orbitals possess C2 symmetry or the center of symmetry. However, these two p orbitals don't possess the mirror plane symmetry because they are not the mirror image of each other. So in those p orbitals in which the same signs of the p orbitals are present on the same side, they possess the mirror plane symmetry, and those p orbitals in which the same sign of the orbitals are present on the opposite side of each other at equal distance, they possess the C2 symmetry or the center of the symmetry. My question is, why the center of symmetry is called C2 symmetry? Why not it is called C1 symmetry, C3 symmetry, C5 symmetry, and so on? The answer to this question is, if an object appears identical after rotation of 180 degree, that is twice in 360 degree, it possesses C2 symmetry. So similarly, if an object appears identical after a rotation of 90 degree, that is 4 times in 360 degree, it will possess the C4 symmetry. So in the case of the p orbital, it will appear to be identical after each rotation of 180 degree, and hence it will appear 2 times identical in a 360 degree rotation. That is why it is called C2 symmetry. Here we have ignored the signs of the p orbitals. Important thing that you may have noticed in my previous examples of pericyclic reactions, that each pericyclic reaction involves a conjugated system. What is a conjugated system? A system that possesses alternative single and multiple bonds in one plane is a conjugated system. So if one molecule possesses a double bond, then a single bond, and then either a double or a triple bond all in one plane is a conjugated system, and so on. Let us discuss the bonding in a simple molecule of ethene. In the case of ethene molecule, the 2 carbon atoms are sp2 hybridized, and each carbon is having the p orbitals, and the 2 p orbitals are on the same plane, and hence they can overlap, and by their overlapping one pi bond is formed. So my question is, ethane is a conjugated or non-conjugated molecule? I am leaving the answer to you. You have to answer this question in the comment section of this lecture. इस स्लाइड पे आप देख सकते हैं कि ये 2 p ऑर्बिटल्स आपस में ओवरलैप कर रहे हैं, और ये ओवरलैपिंग किस तरह की हो सकती है? ये ओवरलैपिंग जो है अकॉर्डिंग टू द मॉलिक्यूलर ऑर्बिटल थ्योरी हम देख सकते हैं कि 2 टाइप्स ऑफ पॉसिबिलिटीज ऑफ ओवरलैपिंग ऑफ p ऑर्बिटल्स इज प्रेजेंट। एक पॉसिबिलिटी ये है कि 2 p ऑर्बिटल इस तरह ओवरलैप करें कि उनकी पॉजिटिव लोब्स आपस में एक ही साइड पे और नेगेटिव लोब्स भी एक साइड पर हों। तो इस तरह की ओवरलैपिंग जो होती है वो कंस्ट्रक्टिव ओवरलैपिंग होती है, और जो रिजल्टिंग जो ऑर्बिटल बनता है उसको हम मॉलिक्यूलर बॉन्डिंग ऑर्बिटल कहते हैं, और ये जो है लोअर एनर्जी का होता है, और इसको हमने psi1 जो है वेव फंक्शन जो है असाइन किया है। इसी तरह दूसरी पॉसिबिलिटी ये है कि दोनों जो पी ऑर्बिटल्स हैं उनकी जो लोब्स हैं वो पॉजिटिव जो है वो अपोजिट साइड पे हैं, और इसी तरह नेगेटिव भी अपोजिट साइड्स पे हैं, और इस तरह जो एक मॉलिक्यूलर ऑर्बिटल बनता है वो एंटी बॉन्डिंग मॉलिक्यूलर ऑर्बिटल कहलाता है, और उसकी एनर्जी हायर होती है, और इसको हमने यहाँ पर Psi2 स्टार का नेम असाइन किया है। तो अकॉर्डिंग टू मॉलिक्यूलर ऑर्बिटल थ्योरी जितने एटॉमिक ऑर्बिटल्स आपस में ओवरलैप करते हैं उतने ही आपके पास मॉलिक्यूलर ऑर्बिटल बनते हैं। हाफ उसमें जो है वो बॉन्डिंग होते हैं और हाफ जो होते हैं वो एंटी बॉन्डिंग होते हैं। यही इस स्लाइड के ऊपर शो किया गया। Now the one very important questions arise: how do the two p orbitals overlap? Answer comes from the molecular orbital theory. According to the molecular orbital theory, when atomic orbitals overlap, molecular orbitals are formed. How many atomic orbitals overlap? It depends upon molecule to molecule. And how many molecular orbitals are formed? It depends upon the number of the overlapping atomic orbitals. Suppose if two atomic orbitals are overlapping, two molecular orbitals will be formed. Half will be bonding and half will be anti-bonding. The bonding molecular orbitals will have lower energy and the anti-bonding molecular orbitals will have always the higher energy than the bonding molecular orbital. So the half of the overlapping atomic orbitals will be bonding and half will be anti-bonding. Always remember that the bonding molecular orbitals will always have the lower energy than the anti-bonding molecular orbitals. So here in this case I have shown a bonding molecular orbital having no node. Node is a place where the value of the wave function of psi becomes 0. So in the case of bonding molecular orbital you may not see any node. So this is a bonding molecular orbital, whereas in the anti-bonding molecular I have shown one node. It possesses one node. It is denoted by Psi2, whereas the bonding molecular orbital is denoted by Psi1. So the Psi2 is possessing one node. Node is the place where the value of the wave function of the electron becomes 0. Where is the node in the Psi2? The space between the darkly colored lobe and the white colored lobe that I have shown with the dotted line. This is the place where is the node. This is the place where the value of the psi function of the whereas the value of the wave function of the electrons becomes 0. So the anti-bonding molecular orbital is possessing one node, whereas the bonding molecular orbital of the ethane is possessing no node. So the electron will go into the bonding molecular orbital first. Here I have shown how the p orbitals, the two p orbitals are overlapped. In the case of Psi1 or bonding molecular orbital, the two p orbitals, the atomic orbitals that are overlapping, have the positive sign bearing lobes on the lower side and the negative sign bearing lobes on the upper side. You may say that the same sign bearing lobes are on the same direction, and hence a bonding molecular orbital is formed by the overlapping of the two atomic orbitals. So what kind of the symmetry these two orbitals possess? I am talking about the orbitals that are involved in the overlapping of a Psi1 bonding molecular orbital. So in this case you may see that these two are the mirror image of each other. You may have the another situation in which the positive bearing signs are on the upper side and the negative bearing sign are on the lower side, and similarly the result is seen. These two atomic orbitals have the design wave function of Psi1 and have a mirror plane symmetry. So what kind of symmetry these two molecular Psi1 atomic orbitals have? They have mirror plane symmetry. So we may say, I have in the chart in the below table I have shown the orbitals on the one column, and in the second column I have shown the M stands from the M stands for the mirror plane symmetry, and the C2 stand for the center of symmetry. So the two atomic orbitals that overlap to form a bonding molecular orbital have a mirror plane symmetry. So in the case of Psi1 I have written the word S. S means they have the symmetry. So I am talking either they have the symmetry or not symmetry. If they have the symmetry, I have shown the word, I have shown it with the word S, and if they don't have any symmetry, I have shown it with the word A. So the Psi1 have mirror plane symmetry, so they are designated with the S. And do they have the center of symmetry? No, they don't have the center of symmetry. So in the C2 column, I have written A. A means absence of symmetry. So the psi1, in the case of psi1 or the bonding molecular orbital, the two atomic orbitals have the mirror plane symmetry and absence of the center of symmetry. Similarly, in the case of anti-bonding molecular orbitals, the two orbitals that are overlapping have the positive signs on opposite direction and the negative signs of the lobes on the opposite direction. Do they have mirror plane symmetry? My question is, do they have mirror plane symmetry? No, they are not the mirror image of each other. So in the case of psi2 star, in M2, in the M column or the M2 column, I have M1 column, I have written the word A, means absence of symmetry. Do they have center of symmetry? Yes, they have the center of symmetry. So if you move from the place center where I have written the sign positive, you go on the opposite direction, you may you meet the positive bearing lobe on the equal distance and the negative bearing sign bearing lobes on the opposite direction. So they have the center of symmetry. So in the row of C2, I have written the F means symmetry with reference to center of symmetry for psi2 star, and in the row number M2, I have written absence, A for absence. They don't have mirror plane symmetry. So in short, you may see that in the case of bonding molecular orbitals, the two p orbitals have mirror plane symmetry and absence of center of symmetry, whereas in the case of anti-bonding molecular orbital, the two overlapping atomic orbitals have center of symmetry and absence of mirror plane symmetry. In my previous slides, I have discussed a very simple case in which the two p orbitals are involved. What happens if three atomic orbitals are overlapped? We know when three atomic orbitals are overlapped, three molecular orbital will be formed. Half will be bonding and half will be anti-bonding. But how you will half the three? 1.5? No. Atomic orbitals molecular orbitals cannot be half. It may be either exist or not exist. So what will be the situation? This situation will be discussed in the coming slides. Here we will discuss when even number of atomic orbitals overlap. That is 2, 4, 6, 8, 10, 12 and so on. So when 4 atomic orbitals overlap, what will be the symmetry among the resulting molecular orbitals and anti-bonding molecular orbitals? Suppose there are 4 atomic orbitals that are undergoing overlapping. So when 4 atomic orbitals are overlapped, 2 will be formed as the bonding molecular orbital and 2 will be formed as the anti-bonding molecular orbital. Since there are 4 atomic orbitals that are overlapping, so total 4 molecular orbitals will be formed, half of which will be bonding and half will be anti-bonding. And these bonding and anti-bonding molecular orbitals are assigned the wave function as psi1, psi2, psi3 star and psi4 star. So half will be star means anti-bonding. So half will be bonding and half will be anti-bonding. What will be the symmetry? You may simply write M1 for psi1, C2 for C2, for psi3 you may write the M1 and M1 C2, M1 C2, M1 C2. This will be the sequence of symmetries among the p orbitals. If you have multiple number of the atomic orbitals that are undergoing overlapping. So in the case of the 4 atomic orbitals are overlapping, psi1 will have M1 symmetry and psi2, that is also a bonding molecular orbital, will have the C2, whereas the C3 will be C3 star, since it will be a anti-bonding molecular orbital. So it will have M1 symmetry, and psi4 star will have again C2 symmetry. So you have to write the symmetries in this sequence: M1 C2, M1 C2, M1 C2, M1 C2. So this is the simple way to assign the symmetries to the p orbitals if there are a number of p orbitals that are overlapping. So you have always to follow this sequence: M1 C2, M1 C2. M1 stand for mirror plane symmetry, C2 stand for center of symmetry. We have learned what is a pericyclic reaction. we learned that those reactions that follow concerted mechanism and the pi electrons in these reactions move in a circular manner are termed as the pericyclic reactions. We have learned the concerted mechanism. Concerted mechanism is that mechanism in which the bonds of the reactants are broken and the bonds of the products are formed through a transition state simultaneously. That is, at the same time the bonds of the reactants are broken and the bonds of the products are formed. So these reactions are termed as the pericyclic reactions. So there are two conditions for the pericyclic reaction. It must have to follow the concerted mechanism and the pi electron must have to move in a circular manner. The pericyclic reactions are stereospecific. It means that under the given set of conditions from a particular reactant, a particular or a specific type of stereoisomer will be obtained. For example, if A and B products are reacting under the thermal condition in a pericyclic reaction and it is forming a C product which is cis form, then whenever you will perform this product, you will always obtain a cis product. You will never obtain a trans product in the given example. So similarly, if some reactants are giving the trans product, they will give only a trans product, preferably under the given set of conditions. Since the majority of the pericyclic reactions involve the p orbital, so the symmetry of the p orbitals is important. If we talk about the symmetry of the p orbitals possess two types of symmetry. Number one, mirror plane symmetry, that is designated with M1, and the number two is the center of symmetry, which is designated with C2. What is mirror plane symmetry? When the two p orbitals are the mirror image of each other, then they possess the mirror plane symmetry, or in other words, when the positively assigned lobes of the two orbitals are on one side and the negatively assigned lobes of the two p orbitals are on the other side, then they are said to have the mirror plane symmetry. What is center of symmetry? Center of symmetry, if the positive bearing lobes of the one p orbital, if the positive bearing lobe of one p orbital is on upper side and the positive bearing lobe of the second or the opposing p orbitals is on the opposite side, and same is true for the negatively assigned lobes of the p orbitals, then these two p orbitals are said to possess the C2 symmetry. When multiple p orbitals are present, you may simply assign their symmetries as M1, C2. First is assigned as M1, second is assigned C2, and third is assigned as M1, fourth is assigned as C2, and so on. Here I have designated the first p orbital as psi1 and its symmetry is assigned as M1. The second is psi2 and its symmetry is C2. And third is psi3 and its symmetry is M1. So you have to simply write the symmetries as M1, C2, M1, C2, M1, C2 if you have multiple number of p orbitals. So this is the summary of the today's lecture that we have learned so far. Here is a small quiz. Draw two different pairs of the p orbitals showing two different types of symmetries. In 2-butane, what kind of symmetry is present in its p orbitals? You have to answer the question number 2 in the comment section only, whereas the pictures of the p orbitals showing different types of the symmetries, you have to email me. My email is m.yaseen, YASEEN@ue.edu.pk. So you have to send me the email of the question number 1 and you have to answer the question number 2 in the comment section of this lecture only. The list of the books that you may read for further understanding of the pericyclic reactions. I personally like the book written by the Robert T.M. Obert N.B. Organic Chemistry, Prentice Hall, New Jersey, 1992, 6th edition. So you may consult any of the books listed on this slide.